Okay, so listen, here is a popular question. The question is, this is the LVB matrix, right? Going from the vehicle to the body. This is the LVB matrix, the transformation matrix. The popular question is this: if I change the order of rotations, what would change in this equation? Well, if you change the order of the coordinates, the rotations, you would still be able to find a transformation matrix that would take you from here to there. From here to there, you would find a transformation matrix. But the transformation matrix would be different if you change the order of rotations. The numbers will be different. The structure might be the same, but the order will be different. Why? The numbers will be different. Why? Because the magnitudes of these angles will be different. Okay? So you could obtain a transformation matrix going from here to here. Going from here to here, you could find a transformation matrix. You could find a transformation matrix going from here to here, but it will be different if the angles are different. Understand that? So the order might also be different. So you might ask, why is the order different? Why is the magnitudes different? Why are the angles different? Well, because the order is different. Look at this. If you had a coordinate system up here, x, y, z, right? You rotate around z and then around y. Well, if you first rotate around y, then the rotation around z might not be the same rotation anymore because the axis is different. Rotate around z and then around y. Want to go to the same place, first rotate around y and then around z, well, it might be a totally different angle now. Okay? Therefore, the order will change. This order will change. The magnitudes will change. And therefore, this matrix will change. But you will still find, if you go from body to vehicle or vehicle to body, you should still go from here to here, no matter which way you choose. But the magnitudes will be changed. And because the magnitudes will be changed, we cannot say theta is 20 degrees, we will not understand the same thing. Therefore, in flight mechanics, it's important we keep the order. And when I say theta equals 20, 30, 50 degrees, whatever, we all understand the same thing. Okay? Yes, please. Yeah. That's right. Yes, it is defined based on our order of orientation, order of rotations. Yes. Okay. Any other questions? If someone defines them differently, let me just put it this way. I haven't quite seen anybody define it differently in my professional life. Okay? If anybody defines it differently in flight mechanics, then he or she should explicitly tell how they define it and why they define it that way. Okay? When we say in flight mechanics, phi roll angle, we all mean this. Nothing else. If we talk about a yaw angle, we mean this. Unless specifically otherwise explained. Okay? Okay, let me take it a little bit back, because in certain cases where, let's say you are trying to build a simulation, and in the simulation Z is pointing upwards because of some other reasons, and someone tells you because Z is up, therefore this is minus or something. These are special cases people should tell you. But in aerospace, most of the time, there's very, very few exceptions that might happen. These are the Euler angles, and this is how we understand it. Especially in this class, this is what we are understanding. Okay? Any other questions? This is something you really have to understand. If you go out there someday, and then if people ask you what is phi, and you just plot this picture and you can't tell anything anymore what the pitch angle is, that would be not good. aerospace engineer has to understand this subject very, very precisely, the way I explained it to you. Is that okay? Okay, so here we are now. Then we can write any vector in the body fixed that could be written from the vehicle, and that is written in the vehicle carried coordinate system. Okay? And that is basically, you write this like that: L3 phi, L2 theta, L1 psi, and we call this V. Okay? So this is psi. Right? So this is that, and we call this one L BV. Now this is all good, but how about this one? How about doing the opposite? Basically, finding the transformation matrix that will take me from the body to the vehicle. I mean, doing the opposite. Let's go to the other way around. Can I do that? I mean, yeah, it should be quite straightforward, just to find the transformation matrix going from body to vehicle instead of going from vehicle to body, because this was the transformation. We went from vehicle, we went to body. So now I have the body. Someone gave me the representation of that vector in the body fixed coordinate system, and I want to go the opposite way and find the vehicle carried coordinate system. So what do I need to do? I just need to do the opposite now, going this way with the same angles, doing the opposite. Basically, I rotated, this one around x2 by phi. Now I have to rotate the x coordinate system. The x3 and x2 is the same now because they are rotated around the same axis here, right? x3 and x2 is the same because it was rotated around x2, so you obtain the same angle. So what you need to do is you just need to take this coordinate system, rotate it backwards in x2, or x3 in this case, by minus phi, of course. This time you go the opposite way. Like plus phi would be, this way. If you go plus phi, you need to go minus now to go back, right? Look up here. If the airplane is like that, you have to, how did we get here? If this was north, you rotate, rotate, rotate. Now I want to go back to the other one. What do you need to do? If this was plus phi, you need to do minus phi, the opposite way. First rotate around minus phi, rotate around minus theta, rotate around minus psi. Right? And then you are at northeast down. So if this was vehicle, and if you are at body and you want to go back to vehicle, you don't go this way, you go the other way. You start here with the vehicle, with the body, rotate around phi by a negative, rotate around this axis by a minus phi, theta, and rotate by a minus psi, and you are back at northeast down. So any coordinate system that's written in body, you could actually do the opposite and find the same vector written in the vehicle carried coordinate system. Isn't that true? Do you understand that? So, which really means, you could be doing this. So you want to go from body to vehicle. So the first rotation would be again a rotation around the x-axis, which is L3. L3 is the rotation around the x-axis, remember? So it will be the rotation around the x-axis, but it will be minus phi. So that would be the first rotation. The second rotation would be L2 again, but it would be in the opposite direction. And then it would be L1 in the opposite psi direction. Okay. The order of rotation, this was 3, 2, 1. Because 1 was, look at this one. Remember I had 3 over here. L3 was the rotation of phi. So I call this the rotation around the x-axis. We called it L3 just to make a difference. Now I'm again doing a rotation around the x-axis, but in minus phi. Minus phi doesn't mean it's a negative number. It just means it's opposite of phi. If phi was minus 10, this would be plus 10. Or if this is plus 10, this would be minus 10. It's just the opposite, right? If this is a plus 10 rotation, this would be a minus 10 rotation. Okay? So you first rotate around the x-axis, then around the y-axis, then around the z-axis, and you are back at the vehicle coordinate system. And this one we would call LVB, meaning the transformation matrix that will take you from the body fixed coordinate system to the vehicle fixed coordinate system. Any questions? Yes.
Inverse matrix, using inverse matrix to get vehicle carried coordinates.
Mm-hmm. So you're asking how I get this?
No. Can we use inverse of the matrix?
Of this one?
Step by step. First L3 minus inverse L3.
You don't need to do the inverse of this one. You just change the order. You can take the inverse of this one. Let's talk. I will talk about the inverses in a minute, okay? Actually, that's exactly where I am. Here's the question. How do I obtain this transformation matrix now? How do I obtain this transformation matrix for the other one? So I need to rearrange everything and re-obtain this, right? That's one way of doing this. Another way is to play around a little bit and do a little algebra. For instance, you could say, you could look at this one. Let me put it on another page. You could say this one is equal to LBV VV. So this is a 3 by 3 matrix here, right? So you could do this. It's equal to LBV over minus 1 times B. So you could take the inverse of this matrix and obtain this thing. Go the other way around. But that is also equal to this. LVB going from B to this. So what I'm trying to say is that LBV is the inverse of LVB. It's kind of obvious, right? I mean, look at this one here. You go from V to B, B to V. All you need to do is take it to the other side. It will become the inverse, right? So it will be this thing. So that means if you would take the inverse of this matrix, you would take this inverse of this matrix, you would actually find the transformation matrix that will take you from body to vehicle. Right? You see that? So you just take this matrix to the other side, it will be an inverse, and it will be that. Now, taking inverses is not really straightforward, not really fun. It's not easy to take an inverse, right? Especially if it's a 3 by 3. But there's a nice property about this matrix I will show you in a minute. But you understand that the inverse is actually equal to that. It also means that LVB inverse is equal to LBV. So if you take the inverse of this matrix, see, basically you're taking the matrix to the other side. I mean, is that clear? And therefore it's the inverse, okay? But there's a property to this, and fortunately we don't have to take inverses. Let me start a nice property here. Let's start with this. Let's take a vector in the B written in the body fixed coordinate system and a vector written in the vehicle carried coordinate system. Okay? There are two vectors. It's the same vector. Because it is the same vector, the magnitudes are the same, isn't it? Is that okay? Magnitudes are the same. It's the same vector. It's just written in two different coordinate systems. One is written in the vehicle carried coordinate system. One is written in the body fixed coordinate system. So because it's the same vector, the magnitudes are the same. If the magnitudes are the same, you can write this property, which comes actually from linear algebra. V transpose times VV. Okay? So you're taking the transpose of that, basically the inverse of that vector. You write it as a row vector, so it will be like this. Let's say it will be like this, x, y, and y. Okay? Let's say this is V. Okay? So what you're doing here is you take this. The transpose looks like this, x, y. Okay? So Vt times V basically means this. xy times xy will give you x squared plus y squared. Okay? So the magnitude of this would be what, if you ask me the magnitude of V, the magnitude of V, I'm just doing this on the side just to explain you this. The magnitude of V would be x squared plus y squared square root, isn't it? Yeah. So this is like, if you do this, V transpose times V will give you x squared plus y squared. Okay? So this would be like this would be like this. Sorry. If this is true, then this is true, which means it's the square of this one. It's basically Vt times V. Understand that? Don't look too baffled. This is just very simple stuff. X, y, and you take the transpose and you multiply them, you get x squared, y squared, and the magnitude would be x squared, y squared square root, so that therefore VTV is equal to the square root, the square of VT. So if this is true, then this must be true. Is that clear? Okay. So let's do a little algebra here. Let's start with this one. This will lead into some really useful property. VV, okay. So let's write the first one here. It's LVB times V transpose times LVB times VB. Right? I mean, you see that this is here equal to VV transpose, and this is equal here to VV. You see that, right? V is a vector written in the vehicle carried coordinate system, and it is the same vector written in the body fixed coordinate system. So it is the same vector. VV and VB is the same vector. One is written in the vehicle, one is written in the body. When I write a subscript over here for a vector, it denotes in which coordinate system I'm writing this. And this one denotes in which coordinate system I'm writing this. I think this is what we agreed last week. So if you start forgetting these things, it's maybe time to review what we are learning in class. Unfortunately, this is all on the web now. The lecture is on the web. You might go and re-listen to the lecture if you have trouble. Okay? Okay, so this is that. So you can write this thing now. You know, the transpose, it will look like this. VB transpose is equal to LVB times VB. Okay? So this is still the same thing. This is still VV. Okay? And this part is just taking the transpose out. I'm sorry, you have a transpose here. So where is this coming from? This is again from linear algebra. If you have A times B transpose, that is equal to B transpose A transpose. Okay? something you have in linear algebra. So it's the same thing over here. This is the transpose. You take it to this side and this side, so it's transpose. Okay, I mean, this is a vector, but it's, you know, so you take the transpose here. So you have this. Okay. So this is that. But this is also equal to, because of this relation, this should be also equal to B, V, B. This should be equal to that because of this. Which really means this part here is equal to what? Is equal to identity, right? It is the identity. So LVB transpose and LVB is equal to identity. So this is a great property because it also means the following. LVB transpose is equal to LVB inverse. You see, if I take it to the other side, it will be the inverse. So the transpose of that matrix, of the transformation matrix, is actually equal to its inverse. Okay? So this is a property of the transformation matrices. A property of transformation matrices. A property of all transformation matrices. Okay?
How can we find 3 by 3 matrix transpose?
That's a good question. How do you find the transpose of a 3 by 3 matrix? I will not answer that question. Please go and find out how you find a transpose of a matrix. Any other questions? So that means the following. VV is equal to LVB B. LV is equal to LBV minus 1 VB. But that is also true that LBV transpose is equal to L times this. Vice versa, LB is equal to LBV times LV, and LB is equal to LVB over minus 1 times LV, and that's also equal to LVB transpose VV. Is that good? Okay, so what is easier, finding the transpose or finding the inverse of a matrix? Transpose is easier, right? It's like that. Okay, I'll answer your question. You take the columns, you make them rows. Take this column, make it a row. Take this column, make it a row. Take this column, make it a row, and that's the transpose. Okay? The columns becomes rows, rows becomes columns, right? So that's the transpose. And that is equal to the inverse of this. It's a very great property. So you have to find this transformation matrix only once. So let's say in the exam, I ask you to find a transformation matrix from the vehicle to a body, okay? And you make your calculations, you do sines, cosines, transformations, you do all this, you find the transformation matrix. In the second question, I will ask you the opposite. Find the transformation matrix going from body to vehicle, or from vehicle to body, whichever. And if you still, again, all you need to do is find the transpose. But if you start doing again the transformation matrices, the sines and cosines and everything, you will lose another 20 minutes, right? And then you will say, oh, there was not enough time. Well, I'm actually trying to test if you know that the transpose is equivalent to the inverse for a transformation matrix. Okay? So this is a very, very useful property, because once you find the transformation matrix from going from one to another, you can do the opposite. Now this is true, this property is true for all transformation matrices that do this, going from one coordinate system to another, doesn't matter which order you follow, right? This property, the transpose to inverse, holds always. The transformation matrix is always, the inverse is always equivalent to the transpose. In flight mechanics, as I said, we go from vehicle to body, body to vehicle. We use this order. If you know one of them, you can use the other one. The transpose is equivalent to the inverse, so that's a very good property. Okay? Because at the end, if you think about it, these are just numbers. I mean, there's a cosine theta, cosine psi, sine phi, cosine theta, you know, all these things. These are numbers. At the end, you will have a 3 by 3 matrix that will look like 3, 4, 5, 6, 7, 8, 9, you know, those numbers. Okay? So let me give you an example. Any questions, first of all? All right. Let me give you an example. Let's say the velocity of an airplane with respect to Earth, written in the body fixed coordinate system, is 900 kilometers per hour. Okay? And let's say this airplane is in this following attitude. The airplane is in the following attitude. Theta equals 0 degrees, phi equals 0 degrees, and psi equals plus 90 degrees. Okay? Here's the question, or the request. Write the velocity vector of the aircraft in the vehicle fixed coordinate system. Okay. Write the velocity of the aircraft in a vehicle fixed coordinate system. So how do we do this? How do we do it? I'll give you body, you want vehicle. Okay? So, do we know how to do this? Can you do it now? Well, we can do this. We can do this, right? But we have to go the opposite way, because it gives me the body, it wants the vehicle, so I need to go the opposite way, right? So I need to do this. I think we already wrote it there. It is looking for this. VV LVB times V body, written in the body fixed coordinate system. So that would be equal to L1 psi, L2 minus psi minus theta, L3 minus phi, or VB, right? Or we could do this. We could take the transpose of this. Take the transpose of this and say V body. Right? The transpose is equal to the inverse, and therefore it should hold. Good. So let's do it. You want to do it? So Theta and phi rotations are 0, and therefore there's no rotation, so everything will be 1 here. Right? There's only one rotation around psi, so it will be only this rotation. So we are looking at the inverse of L1 psi. Can you find L1? The rotation of L1, basically the rotation around what axis? Z-axis. We are looking at the Z-axis. This was the very first rotation we did in class. Remember the very first rotation we did in class? This one, rotation around the Z-axis. So, we are looking for cosine 90, sine 90, 0, minus sine 90, cosine 90, 0, 0, 0, 1. And actually we're looking at the transpose of this, right? Because this was L1 of psi. And we are looking at 900, 0, 0. So what is this matrix equal to? Cosine 90 is sine 90, 1, 0. Minus sine 90, minus 1. Cosine 90, 0, 0, 0, 0, 1. Is that correct? 900, 0, 0. This is the transpose. Now you need to take the transpose of this. Okay, take the transpose. 0, minus 1, 0, 1, 0, 0, 0, 0, 1, 900, 0, 0. So what do you get? Zero, 900, 0. Is that correct? I don't know. This is the result. You multiply 1 with 900. This was a transpose. Now it's not the transpose. I took the transpose. Is that okay? Please go through this at home if you don't understand this. I mean, I know it's a third hour and you might be tired and everything, but I'm not really doing anything very difficult. I mean, it's something that the difficult part is over. This is just algebra now. Just have to understand that this is the transformation matrix, B to V. We already established that it looks like this if you go from body to vehicle. But that is also equal to vehicle to body. This is vehicle to body, but you take the transpose. It's the same. And therefore, I take the vehicle to body, this is 0, this is 0. 0 meaning that the angles are 0, and therefore I only take the psi, so it's only this. So you need to write this, take the transpose, and this is your result. This is not the transpose? What is it? Oh, this one? Yeah, because of that transpose is here. That's why I wrote the T.
Just type down transpose instead of VB transpose. It's going to be VB.
Oh, yeah, okay. You mean this one, right? Okay. All right. Okay? Yes. Can you try it in English, please? Yeah. Vehicle carried coordinate system. Vehicle, okay, sorry, yeah. Vehicle carried. The question I said vehicle fixed, that's not correct. It's vehicle carried coordinate system. I think I'm getting also tired. Okay? Vehicle carried coordinate system, sure. Okay, here is that fine? So let's think about this for a second, what we found. I could do this. Let's think about it for a second, what we have found, or look at the question, better to say. Okay, this was the question. And if you think about it, this is the airplane. It is at 0 theta. Okay, and it has, this is the center of gravity, this is your x body, y body, and z body, okay? And because psi is 90 degrees, in which direction is the airplane flying? It's flying where? Towards y? X or y? X. XV you mean? Is it flying towards north? XB. Yeah, of course XB, but in the vehicle carried coordinate system. East. It is flying east. Why is it flying east? Because psi is 90 degrees. What does it mean? We start from the vehicle carried coordinate system, so the airplane is pointing towards north, 90 degrees, a positive 90 degrees. Z is down, positive 90 degrees. You go this way. North, east, down. Which way is it flying? East. Okay. So if I take a picture like that, what should be this? The green one? It should be pointing east. Okay. So this would be YV. It is pointing east. Okay? And because this is all 90 degrees, this is pointing downwards, this is ZV. Which way is pointing XV? Into the plane or out? Out of the plane. Why is that? Take your right hand. Go from X to Y, Z is pointing down. Therefore, X is pointing towards us, right? So I'm going to plot it like that. X is pointing towards us, XV. So now we have the body fixed coordinate system and we have the vehicle carried coordinate system. Basically north, east, down. Which way is north? This way, around X. V, that's north. Local gravity vector east. Now we have the whole picture. Okay? All right. What was the velocity of the airplane? Body fixed coordinate system. It was 900 kilometers per hour towards X body. Right? Because this means it's written in the body fixed coordinate system. So therefore, this was the direction of the velocity vector. And this was 900 kilometers per hour. Right? Towards X body, that's what the question says. Which also means the velocity of the aircraft with respect to an observer from Earth, written in the vehicle carried coordinate system, is simply 900 is towards YV. So it is 900 kilometers per hour. I can see it in this picture. What did we find? We found the exact same thing. Going through this. Do you understand what this now means? Here's the picture. How did I come up with this? I just wrote it geometrically and found the same thing. Now, of course, this is now an easy problem and we can plot it and immediately write it ourselves. But if the problem was a little bit more complicated, then you cannot plot it and it's difficult to see it geometrically. Then this is very useful. Doing it this way would be very useful. If you want to try something at home, I mean, your homework is on the website, as I said, and your homework has a question like that in your homework, right? So if you do it should be really easy to do the homework, by the way. I mean, it's not a long homework. So this part, you're exactly asked to do this. For example, if you had another example, you could be doing this. X body, Y body, Z body. And I could tell you the airplane has this velocity, v body, and I tell you this is xv and this is zv, and I tell you this angle is 30 degrees. And I tell you no roll. So, find Euler angles. What are the Euler angles? Well, because it's no roll, first of all, phi is equal to 0, right? Well, because it is flying towards, oh, I didn't tell you, no, I did tell you, xv is this way, so which way is it flying? It's flying south. This is north, so this is south. So what is psi? What's the angle psi? This is north, look up here. This is north, the airplane is flying this way. Which way is psi? 180 degrees. So which way do you go? You go this way, 180 or minus 180? It really doesn't matter, but in flight mechanics we use minus 180, and I will tell you in a second, and therefore theta is immediately 30 degrees, I can tell you from this picture. Now, one more thing before we leave. In flight mechanics, these are the definitions for psi. So if it is 180, we use minus pi over 2 theta pi over 2. So theta can be that. And minus pi phi for pi. So we always use the negative ones if it is in the border of minus or plus, which way you want to go. Okay, so this is something that you need to remember for the extreme cases where something is 180 or 90 degrees. So you might ask why theta is only 90 degrees and not 180, because everything else is 180. Because, let me go up here. Theta 90, this is theta 90, right? This is theta 90. So if it was like that, you wouldn't do this. If the airplane is like that, you actually would do this. Go this. No. If it's like that, I would actually go here, do this, and then do that. You see? I'm trying to answer why theta is not 180 to 180. It's not from pi to pi, from minus pi to pi. Because, this would be pi over 2, 90 degrees, right? So if the airplane is in this condition, you don't need that theta that's more than 90 degrees. If the airplane is in this situation, you would just do that, do this, go here, go up, and do this. Okay? So therefore, you don't need more than 90 for theta. Any questions? Okay, do your homeworks, and in about 2 weeks we will have our exam. Okay? Not next week, but the following week. I will tell you the date.